So go ahead and create a new notebook. I'm going to give this a title, call it Potential Flow Building Blocks in Class. Okay. Now, I always have what I call my boilerplate for the vast majority of my Jupyter notebooks. I usually copy and paste them from other existing notebooks, or just kind of type them up here. So import NumPy as NP. Okay, so that's the NumPy library that's going to give you these NumPy arrays. And for plotting, import matplotlib.pyplot as PLT. So you know what the as means. You're giving a nickname for this library, so that every time you have to create a plot, you don't have to call matplotlib.pyplot.plot. You just call plt.plot. Instead of calling numpy.createArray, you say numpy np.createArray. Okay. I'm pretty sure you guys are have figured this out already. Okay. So now I want to embed figures in the notebook. Okay. So there's some magic here that I do. Matplotlib inline. So this symbol, the % symbol, is called Python Magic for Jupyter Notebooks. Allows you to do some cool tricks in Python. Now, this next one is my coolest trick. And if you haven't done that, don't walk another day on Earth without doing that on your notebooks. Okay? Inline backend dot figure format equal SVG. Okay? Now, many of you have not done that. Let me show you what this does. Okay, so I'm gonna pretend that I'm plotting something. I'm gonna pretend that I'm plotting sine x. Okay, so I'm gonna create a distribution of points, linspace, just like in MATLAB, from 0 to 3.14. Okay, and 100 points, and then I'm gonna plot sine x. Okay, so x mp.sine x. Okay, that's nice. Now, if you zoom into this one, this is a raster image. See the pixels over here? Now you're seeing this. If you think this is good resolution, it is not. This is horrible resolution. This looks good only on this screen because the screen is low resolution. You go and print this one, it's going to look like crap, or it's going to look this size at 300 dpi. So there's no excuse not to create vector quality graphics. Vector graphics are like fonts. Now look at this font. I zoom in, right? See this font? It's not pixelated. Why? Because it's a vector graphic. So there's no excuse not to create vector graphics. This magic line here allows you to make all of the graphics you're visualizing in Python to look like vector graphics. SVG stands for Scalable Vector Graphics. Scalable because you can stretch them, shrink them. They will always look impeccable quality, infinite resolution. Okay. So now see what happens. Going to make it an SVG. I'm going to print this. Now look at this. I'm going to zoom in. It's going to look 100% beautiful. Okay. Anyway, so that's for the boilerplate. Okay. Going to kill this one, and let's start working on doing something. So here I want to plot the streamlines of a uniform flow. Okay, I'm given C. What is C? It's behind here. It is u infinity y cosine alpha minus x sine alpha. Okay, so now I need to plot this on an xy plot. I need to plot contour lines of C. So I need the machinery to do a contour lines. To do contour lines, you need a grid, x and y points, right? So that you calculate the function values at all of those points and then ask Python to create contour lines or streamlines. Okay? So let's start by doing that. First, I'm going to define some properties of my grid. Now you can play with those as much as you like. Doesn't matter. I'm going to create a grid of equal size and equal number of points in the x and y direction. I'm going to call that number of points is, let's say 200 points in each direction. Number of grid points in each direction. Okay? And then I'm going to define the extent of my domain. x0, let's plot from -2 to 3, and y0 from -1 to 1. Okay? So that's the extent of my box where I'm going to be plotting. Okay, so I'm creating a box. I'm going to create a box that looks like this, from x0 to x1, and from y0 to y1. And now I'm going to discretize this. I'm going to split it, create a bunch of points. Okay, a bunch of points, 1, 2, 3, 4, etc. N points in each direction. Okay, so that I can place function values on it and create contour lines. Wonderful. Okay, there's an easy way to do this. I'm going to create 2 linear spaces, one for the x-axis, one for the y-axis. Lin space is just a sequence of points. Okay, so x coordinates are going to be np.linspace from x0 to x1 with n points. Okay, what the heck is linspace, you ask? If you're in doubt, there's a sentence in numerical methods that we repeatedly say. If you're in doubt, print it out. Okay? So, what is linspace? Print x. It's just a bunch of points, man. Bunch of coordinates. Starting from x0, which is -2, and then the next point, all the way to what? 3. Look at that. It's an array of points all the way to 3. They're all equally spaced. There's 100 of them. Okay? Now, it seems silly to print with 150 points because you can't see a damn thing. So do 5 points, man. Look at that. -2, -0.7.5, etc. Okay? So that's x. Let's do y as well. So with y, we're going to go from y0 to y1 with n grid points. Okay, so now I created a lin space in the x direction, created a lin space in the y direction. Now I need to convolute them. I need for every point in x to have all points in y. So I need to combine them together so that I have a 200 by 200 grid, or an n by n grid. So you do this with something called mesh grid. How do I know mesh grid? I Googled it. Like, how do you create a grid in Python with lin space? Seriously. Or go to ChatGPT. Or ask someone, right? It's okay. All right. So if I do np.meshGrid, and I give it x and y, now how do you know what to give a function? There's a little neat feature in Jupyter Notebooks. You see when I come close to that parentheses over here, it highlights it in green. I'm away. It highlights it in green because it tells you, shows you what if there's a matching parentheses for it. But also when you are there, if you press Shift, hold on, where am I? Okay, if you press Shift Tab, it gives you the documentation for that function. You've never seen this? Docstring, yeah. Shift Tab, if you press it twice, it even expands it. Oh, look at that. Wow, this is the function signature. What is the function signature? It's the documentation of the function. What do you do with that function? How do you use it? Okay, it makes an n-dimensional coordinate array of vectorized evaluation, blah, 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 whatever. Essentially, it takes a bunch of arrays and convolutes them together so you create a 2D grid, 3D, 4D, ND grid. So in other words, for every point x, I want all the points of y. Another point x, all the points of y. Another point, all the points of y. Okay? Creates a grid. Now what matters to me is what it's going to return. Okay? So let's see. If I scroll down, it should have a return value. If I process something in this function, it's going to return to me the x and y coordinates of the grid, or the x, y, z, w, whatever, of this grid in all directions. Okay? So here's what I'm going to do. I'm going to store this mesh grid in new capital X and capital Y coordinates. Okay? Now, what is capital X? What is capital Y? Print it. So let's go back to 5 points. If you print X, okay, it's going to show you for the first Y value, for Y equals 0, we have all of the X values. For Y equal 1, we have all, for the next Y, we have all the X values. For the next Y, we have all the X values, and so on. Same thing for the Y grid. Okay? So it's and it's of size n by n, which is 5 by 5, 25 over here. Okay. So you need this to plot any kind of contour, okay? Any kind of contoured function. Okay? If you have a function that is three-dimensional and takes x and y, and you don't want to plot a 3D, you want to plot a contour levels of this function, this is what you need to do. Okay? All right. So let's say I want to plot the function z equals sine x times y. Okay? Sine x times y. Let's do that. plt.contour. I'm going to give it now. Contour, what does it do? It needs to take x, y, and z values. Okay? So I'm going to give it capital X, capital Y, because that's the grid. And I'm going to call my z function, which is simply np.sine x times y. Ah, look at that, beautiful. Man, Python is cool and easy, right? How do you know these syntax? You don't. You Google them. You ask chat. You ask your friend. But you have to know what you need to do. How can I create a contour plot of a three-dimensional function? That's how you do it. Now, there's a bunch of options here for contour, like the number of levels, and if you want to label the levels, etc. We don't need to worry about that right now. Yes?
Is this B or psi?
This is just an example.
Oh, just an example.
Yes, just an example to demonstrate how I can plot a contour. Okay? Okay. So now, in this notebook, we will create and plot building blocks of potential flow functions. For a uniform flow, we have, if you haven't done this, that's another powerful tool of why we use Jupyter Notebooks in our department. It's because you can write a report with your code. For a uniform flow, we have C of x, y is equal to some u infinity, okay, times, what was the formula? Y cosine alpha minus y sine alpha, right? So y cosine alpha minus x sine alpha. Oh, typo here. Now look at how beautiful this is. My numerical method students, if they don't have text like this in their notebooks, they get 0. Because I don't know what they're doing. I'm not reading their code. Now imagine you as a grad student, you're asked to write a report and you just give code. You'll be fired. Okay? This is very useful for others to understand. Wouldn't you expect this from me as your teacher? If you imagine I just give you a notebook with code. I'm like, what is he giving us? What the heck? I don't understand the damn thing, right? But it's good to document. It's good to write what you're doing. Now, in this demonstration, I'm going to skip a little bit on the writing because I don't want to spend my time writing things. But I'm just hoping to encourage you to write what you're doing. Okay? All right, so how do we do this now? Clearly, this function, I'm going to create, what I would like to do is create a function that I can call left and right. I want to be able to call psi and give it x and y and alpha and u infinity, and for it to return a bunch of numbers, and then I want to create a contour. Okay? Let's do this. Very simple. Okay? Okay, so here we're going to create or define a function for the stream function of uniform flow that takes in u infinity and alpha as input parameters, as well as x and y. I'm going to define, call it uniform flow. It's uniform flow, or uniform. It needs, I need to compute psi, I need to know x, y, u infinity, call it u inf if you want, and alpha. Result, I always do this in my functions. I always create a variable called result. It's a jar. Put things in it, and then I return it when I'm done. Okay? So in this case, it's pretty easy. It's u infinity times y times np dot cosine alpha minus x times np dot sine alpha. Return result. The best code you will write in your life. The best code you will write in your life is the code that looks like your math. Okay? The closer your code is to your math, the more readable, the more you can remember what the heck you were doing 5 years ago, and the more your posterity are going to understand what you were doing. Okay? Don't create variables like obscure variables, like a variable abscjibra or xkcd. Don't create crap like that. Create useful variable names that can be understood, even if their names are 15 meters long. Maybe not 15 meters long, but create usable code that is readable. You're lucky you're writing code in English instead of assembly. Use it to your advantage. Make it expressive, right? Imagine you're writing assembly code. It's a nightmare. I had a homework on that in my CS class. I didn't do it because I'm like, I don't care about learning assembly. I don't want to do it. Give me 0. Okay. So now, here's my claim. This uniform stream function, if I give it numbers, so for uniform flow, I want to compute psi at x equals 0.1 and y equals 0.3 with u infinity of 10 meters per second and an angle of 0. It's going to give me a number. This is going to give me the value of the stream function at that point. Okay? If I change the number, it's going to give me a different number depending on where I'm at. So now imagine this uniform stream function, if it gives you a number for any combination of x and y, we can apply it to all of these x and y's. Should we do a for loop? No, if you think you're going to have to do a for loop, you live in the past. No more for loops in Python. Why? Because everything in Python is already vectorized. And here's the trick. If you've used NumPy arrays everywhere in building your code, the NumPy arrays are consistent with other NumPy arrays. Any operation on NumPy arrays is automatically done element-wise, like in MATLAB. MATLAB created this thing early on. This is not C++. In C++, you would have to loop. This is not C++. It's vectorized. Even modern C++ can vectorize things. So here's what I'm going to do. I'm going to create C total, I'm going to call it, equal uniform flow on all of x and y with a u infinity. Okay, let's do u inf is equal to 10. So u inf at an angle of 0. What is psi total? Print it. It's hundreds of numbers. Specifically, 200 by 200. Because we've taken uniform flow and apply it to each and every combination in x and y. Now my claim is that if I plot the contour of psi total, it's going to give me nice straight lines. Let's do that. plt.contour. I want to plot it on the grid xy. And I'm going to plot psi total. Drum roll. Ooh, look at that. Gorgeous. Horizontal lines. Let's turn them at an angle, right? So let's delete this guy. Now put an angle, 0.3 radians. Oh, look at that. The flow is turned, 0.3 radians. Okay, now, because of what I want to do in the next few, lectures, I also need the velocity field, u and v, okay, not just psi, okay, because there's another nicer way to plot these contours called stream plot. It's a more beautiful way of creating streamlines. So I would like for each one of those functions to also return a velocity field, okay, u and v components. So for this uniform flow, u is equal to u infinity times np dot cosine alpha, alpha, okay, and v is u infinity times np dot sine alpha, okay, and I want those to be returned with my function. So instead of just returning result, or I'm going to call it psi now, I'm going to return u, comma v, comma psi. So now my function will return three values, three variables. And when I call it, I need to store that return into three different arrays. That's all there is. But there's a little problem over here, because this u is a single value, single scalar value. It's true everywhere on the grid, but it's still a single value. And if I wanted to play well with the grid, I need to have enough points of that same value on the entire grid. Does that make sense? So I need to have this value of u at each and every one of those points. At each and every one of those points. Okay? So what I will do is I'm going to, let me see actually. Well, yeah, I'm going to need to multiply it by an array of the same size as x or y, okay? Just an array of ones. np dot ones like x. If you don't understand what I'm doing here, just do it. Don't worry about it. What this does, so I said I want to have this same value replicated over each point on this grid. I'm assuming x and y are same size, okay? So I'm going to multiply it by an array of ones, just one. So u infinity times cosine alpha times 1 is u infinity times cosine alpha. But I'm going to replicate it over the entire grid, okay? And so I multiplied it by a NumPy array of ones. Now this array looks like x, so I don't need to figure out the dimensions of x, right? The array size of x. So Python gives you that sort of flexibility. Okay, so that's our first building block. We are going to switch back to the board. Let's see if I can pause the recording. I'm not going to pause the recording. Okay. Okay, let's look at our next building block, and soon we will have something really cool if I can finish this in time. Okay, so no questions, please. Okay, for this next building block, oops. For this next building block, we're going to create a source or a sink. Sink is the sink in your, tub, or source is the opposite. It's when you have a leak and there's water coming out from the hole, and it's bad. Okay. So, whoops. The idea is you have some flow coming out from a point that extends, there's a line going from minus infinity to infinity into the plane that's kind of spewing some volumetric flow, V dot per unit length, okay? V dot over L, that's some meter squared per second, some flow coming out from this point, okay? Or going into it, okay? And so we ask ourselves, how do we get the velocity potential for this flow? Well, we can compute the radial and tangential velocities. For this flow, because it's strictly emanating from the center, there's no radial component to it. And also, we don't want to make it rotational, so we're just going to make it just flowing out radially. Then there's only a UR component, okay, at any distance r from the center. At any distance r from the center. So conservation of mass tells us that this volumetric flow rate per unit length, or meter squared per second, is equal to 2 pi r. So at any radial position r, okay, 2 pi r times UR, mass conservation. UR is constant along this entire radial position. So that tells us that UR is V dot over L over 2 pi r. I like to call this a strength, call it M over 2 pi r. Okay? This M is strength of source or sink. If M is positive, you have source. If M is negative, you have a sink. Okay? So now we do the same procedure to deduce the stream function and the velocity potential. For polar coordinates, UR is d phi by dr, and that's equal to M over 2 pi r. And U theta is 1 over r d phi by d theta, and that's equal to 0. There's no angular velocity component. So this implies if you integrate this, you get, so some of them integrate the stream function, you get phi is equal M over 2 pi log r plus a constant, which is 0. Yes, there's a singularity at the center. I don't care. This is an approximation. Don't go to the center if there's a singularity at the center. Stay away from the center. Use another model at the center. If this works everywhere in the flow except at the center, yeah, I'll take that. It's an approximation. Live with it. Equivalently, the stream function, which is pretty useful, is the complement of that. It's M over 2 pi times theta. So the stream function, if you think about it, the stream function, these are the lines of constant stream function. They only change as you go around theta. Okay, these are lines of constant stream function. Lines of constant phi are going to be perpendicular to that. They're going to be these circles. Okay, log r equal some constant. Okay. I want to get to the source or sink. Okay, so we have about 10 minutes. Let's see if we can do it. Okay, so now this poses a problem for us in our Pythonification of potential flows. This poses a whole problem because we need to convert everything into Cartesian coordinates. It's not a problem. It's just you got to do the conversion correctly. Okay? So here's my plan. I think one way of implementing this is to actually define theta and r, or just theta, in our function in terms of x and y, and just use the formula m over 2 pi theta to return the stream function. Okay? Simple? Easy? Let's do it. So similarly to what we did before, for uniform flow, we have this. Now for a source or sink, we have the begin equation and equation. Psi, which is going to be just a function of theta, is equal to m over 2 pi times theta. Agreed? Okay, so let's go ahead and do it. Define def source or sink. Just going to call it a source. It always needs x and y because we're going to evaluate the stream value of the stream function at some point x and y. Okay? I'm going to do x, y. Okay? And what do I need for the source? I need strength, m. If m is positive, you have source. M is negative, you have a sink. Okay? All right. So now let's create a theta. So first, convert theta to Cartesian coordinates. And create theta. Here's a little trick. If you type backslash theta and press tab, you get a theta symbol. Nice. Okay. So theta is the inverse tan of y over x, right? So that's the definition of an angle. If you're at a point xy, theta, the angle, is inverse tan of y over x. Okay. Now, which inverse tan? We need to be able to know in which quadrant we are. The inverse tan does not distinguish the quadrants. Okay. So if you apply inverse tan to some angle between 0 and pi over 2, or between pi and 3 pi over 2, it doesn't tell you which quadrant you are. It gives you the same angle. So because arctan is only between minus pi over 2 and pi over 2, the definition. But there's another tan function that tells you, that runs from 0 to 2 pi, tells you which quadrant you're in, okay? And it's called arctan 2. That's it. So arctan 2, what it does, if you look at the documentation, it gives you the element-wise arctangent of x1 over x2, choosing the quadrant correctly. If you were to go to arctan, it doesn't give you that. Just trigonometric inverse tangent. So we really need arctan 2 to get our numbers correctly. And this is going to be y over x. And then my psi, oh, look at that. I can write psi. Psi is m over 2 pi times theta. Return psi. If you're ahead, go ahead and plot the contours for this psi. If you're still typing, I'll wait for you a minute. Yeah.
So this will plot all the values for C along theta?
For psi along theta, yes. So here's what I did. Because I'm only working with xy coordinates, I don't want to deal with convert outside. I want to convert. I want to use this nice little definition, okay, and just use an xy, and it will plot it over the entire xy plane. So it will pick an xy value, figure out what angle you're at, and then compute the value.
But your XY coordinate may not fall on theta, right? Or does it?
You can define a theta angle for any point. This is
Oh,
the,
that's right, because we're plugging in X1. Sorry.
yeah, because you're at the right from the origin. From the origin, if this is point xy, right? Draw that line. That's theta. For this x1, y1, this is theta 1, etc. Okay. Figures this out. Okay, let's do it. PLT dot contour. Oops, contour of x, y, and source. I'm gonna give it a source. Let me execute this first. Okay, so now I'm going to call source on xy with a source strength of 1. Oh, and I get an error. np.arctan2. Oh, what is this? Oh, not y over x. Y comma x. Sorry. Okay, look at that. Let's add some levels. Bunch of levels. As we expected over there, our stream function was lines emanating from the center. What do you think is going to happen now when we add a uniform flow from the left? It's going to deform these lines like this. Like this, yeah? Let's see. Okay. Now let's combine. I'm going to convert this into a text function. I'm going to do uniform flow plus source. I'm going to define C1 is equal to uniform flow with, on the grid xy, okay, u infinity, let's call it 1 meter per second. I'm creating a uniform flow with u infinity and at an angle 0. Okay. Now source m is equal as to 1 as well, for lack of any other number, meter squared per second. Okay. And psi2, that's the psi function corresponding to a source, x, y, m, right? So that's our function for the source. It takes x, y, and needs a strength. You guys with me? Okay. Still typing? If you're still typing, I'll wait for you. I'll add some comments here, and I say this is uniform flow. Now this is going to throw an error. Can you say why? A what? Yes. Okay. Now this is still going to throw an error. Because my uniform flow function returns u, v, and psi. Okay, so if I type this, oops, hold on, psi, uniform, I didn't throw an error.
Yeah, you have a tuple inside one now.
Well, it should still throw an error. Okay, u, v, psi, 1, okay.
If you tried to add them,
It will throw an error if you add psi1 and psi2. Yeah. Okay. Anyway, so let's just to be consistent here. Okay. If I added them, it will throw an error. So this is uniform flow. We agree. This function uniform is returning 3 quantities. I don't care about uv right now. I care about psi1. And the source function is returning a psi2. Now I'm going to combine them. Combine. Psi total is equal to psi1 plus psi2. Superposition, that's superposition. Okay? Now let's plot the contour. Whoops. X, Y, psi total. Oh! Look at that. Isn't this cool? That's pretty cool. Right? That is so cool. Let's add some more levels. Darn it, that's pretty cool.
What's your U infinity?
What?
What's your U infinity?
1. So we can increase u infinity, go to 10. It will squeeze those streamlines a bit more, right? It squeezed them. Then I can increase the source to resist that incoming barrage of flow. Doesn't matter. Now,
So is this
yes.
in terms of u and v or psi?
This is psi. Yep, the stream function. Okay. Now, these are values of the stream function because it's easy to visualize the stream function. You can't visualize u and v. You'd have to put a vector plot for u and v, or what's called a stream plot. But next, we're going to compute u and v for the source, just like we did for the uniform flow. Okay, and return them and add them together. But before we get there, let's just work with the stream function. Now, this looks like it's the flow over some object here, right? This, in fact, this object defined by this streamline and goes to infinity is called a Rankine half-body. Potential flow is designed to mimic real flows. Some people might say, neglect the bottom, and this is the flow over a hill. Can they do that? Well, I'm not going to arrest them for it. Their model might be wrong, but it's still a better calculation than what you have, right? You know what I'm saying? So it's a model, guys. It's a model, very rudimentary, but it's pretty cool. It's pretty neat. Okay? Now, each one of those streamlines is a wall as far as the other streamlines are concerned, because no flow can cross a streamline. So the fact that I chose this to be my hill is arbitrary. I could have chosen this one to be my hill. Doesn't matter. Or I could have chosen this one to be whatever, my sink. Okay? Or my wall over here. Or this one to be your wall. Doesn't matter. It's a streamline. It's very visual. Potential flow is very visual. These building blocks, now you see the power. Maybe we can combine a couple of sources, or a source and a sink. What happens? And put uniform flow. You're going to get weird shapes. If they resemble a real shape, great. If not, add more of them together and do some math to figure out kind of how you combine them together to make a certain shape. Okay? On Monday, we're going to learn how to move. Now, we place the source at the origin. Okay? But what if I want to place it here? What if I want to place a source here and a sink over here? We can't do that right now. We don't have the math. So we have to improve our derivation and move to be able to move these building blocks to an arbitrary point in space. And that becomes truly powerful. Then we're going to put a source and a sink. What's going to happen? Flow is going to go up from the source and into the sink. Now you have an oval. Then we're going to bring them closer to each other. And you're going to have a black hole. You bring them closer to each other. Okay, we're going to bring them to each other and increase their strength and sink at the same time so that they don't annihilate each other. And you're going to get a cylinder. It's really cool stuff. Okay, we'll do that on Monday and Wednesday. Bring your laptops.